Now we are going to explain the most important thing regarding the lasing action of this gallium arsenide semiconductor. Okay. Now there is a depletion region. What will happen is the reverse forward biased means the depletion region will become smaller and smaller and smaller. So the electrons will come here in this direction, holes will come because it is pushing from both sides. Forward bias means it is pushing from both sides. So what will happen? The junction will become thin. The junction or will become thin. But the reverse bias means junction width increases. Okay, width increases. Actually, we don't want this. This junction width we don't want increase. We want this one only. It has to become thin. So this is the junction actually. See, this is the depletion region. That region is called depletion region, and we have to reduce the width. So you can see that there is no within the depletion region. So now this is the energy diagram. Okay, this is the energy diagram with the and the depletion region. This is very important because this energy diagram is entirely different from the what we learned in the previous cases. So in the energy diagram, you have to mention conduction band energy level. V means valence band energy level, and F means Fermi level. So this Fermi level, actually this at equilibrium condition. That means at the equilibrium condition means we are not adding any extra source. Not we are keeping it at room temperature, room standard atmospheric condition, room temperature. We are keeping the semiconductor means normally the electrons will be like this. Presence of electrons will be below one level called Fermi level. This Fermi level means at the equilibrium condition, there is no external potential applied, and area below the Fermi level is considered to be full of electrons. So here, this is the Fermi level, and you can see that. So this is the Fermi level. This is the Fermi level, and below that you can see full of electrons, full of electrons. Area below which the Fermi level is considered to be full of electrons. So you can see there is no electrons in the depletion region. Actually, we have to increase this. So this is the conduction band. Actually, the electrons population has to be very high in the conduction band for the lasing action to happen. In the conduction band inside the depletion region. That is important. So the lasing action to happen means this region should contain more number of electrons. That is in this region means what? It is above the conduction band. See, easy. So here more number of electrons has to be there for the lasing action. Then conduction from the conduction band, the electrons will be stimulated to the valence band. While going to down to the lower energy level, it will eject the photon together with the stimulated photon, such that so that the lasing action will happen. So how the number of electrons in the depletion region above the conduction band can be increased so that population inversion can be achieved. Now the electrons are below the Fermi level, and it is here it is above the, you can see in the n side electrons are there above the conduction band, but p side no electrons. Even holes are also below the valence band. So actually we have to bring these electrons here. So how we can we have to we will reduce the width of this depletion region with the help of external source. Now in this situation we can see the slope reduced. That means the width of this depletion region reduced as by applying what when we after applying the external source. Actually we applied the external potential and we reduced forward biased in the manner of forward biased. Actually we applied the potential so that the semiconductor is forward biased and the width of the depletion region is reduced, and once the width is reduced, the more number of electrons within the depletion region are excited and reach the conduction band where it is similar to the what metastable state. This is the metastable state, and from the metastable state now one electron we can, if one photon is coming and it will, if it excite or stimulate this electron, then it will go down and it will combine with the hole here. That is what is happening in the semiconductor laser. So we are adding, we have, first we discussed about the p-n junction, p-type semiconductor we discussed, n-type semiconductor we discussed, then we discussed about the p-n diode. P-n diode means we are combining p-type semiconductor with a n-type semiconductor, and once we combine the p-type with the n-type, what will happen? The holes and the electrons and holes will merge, and combination of the electron hole will happen, and at the junction only positive and negative ions will remain. So the existence of positively charged ions and negatively charged ions at the junction will generate an electric field from positive side to negative side. So whenever an external power supply is provided, if the electron flow in the same direction as that of the electric field, then it is called as forward biased condition. And whenever the electrons flow in the opposite direction, or current flow in the opposite